In 1905, Albert Einstein discovered something terrifying. He realized that if anything could travel faster than light, the entire universe would fall apart. Cause and effect would become meaningless. You could receive messages before they were sent. You could kill your grandfather before your father was born. The laws of physics would collapse into paradox and contradiction. This is why the speed of light isn't just a speed limit, it's the fundamental law that holds reality together. For decades, physicists built their understanding of the universe on this sacred principle. Nothing, absolutely nothing, can go faster than light. But then, in 1935, Einstein made a horrifying discovery. The new theory of quantum mechanics, the most successful theory in the history of science, completely violates this rule. Quantum mechanics allows influences to travel faster than light. And here's the truly shocking part. Einstein was right. 30 years after he first raised the alarm, a physicist named John Bell proved that faster-than-light influences are real. They exist. They're happening right now, all around you. When scientists finally ran the experiment to test this, they found something that should be impossible. The universe really does break its own speed limit. We have found a way to travel faster than light, and it's been hiding in plain sight inside quantum mechanics this entire time. Let me take you back to when Einstein first realized the problem. It all started with gravity. Isaac Newton had proposed that gravity acts instantly across any distance. If the sun suddenly disappeared, Earth would immediately fly off into space. There would be no delay. The gravitational force would vanish the instant the sun did. But Newton himself hated this idea. He wrote that the notion that one body may act upon another at a distance is to him so great an absurdity that he believed no man who has a competent faculty of thinking can ever fall into it. Newton knew action at a distance was absurd, but he couldn't figure out what was wrong with it. That remained a mystery for over 200 years, until Einstein came along. Einstein discovered that observers moving at different speeds can disagree about when events happen. Imagine you see two things occur at exactly the same time. An observer speeding past you would see it differently. To them, one event happened first, then the other. Both points of view are equally valid. There's no absolute time that everyone agrees on. Time is relative. But when Einstein applied this insight to Newton's theory of gravity, he found something catastrophic. Say you see the sun disappear and Earth fly off at the same instant, just as Newton predicted. The other observer, the one moving past you, sees something impossible. They see Earth flying off first, even while the sun is still there pulling on it. To them, it looks like cause and effect are reversed. The effect happens before the cause. This is a genuine paradox, a logical impossibility. The only way out was to reject the assumption that started the whole problem. Gravity cannot be instant. There must be a delay. It took Einstein 10 years to fix this issue, and in the process, he completely overhauled our understanding of gravity. In his new theory, general relativity, gravity is caused by the bending of space-time. When there's a change in gravity, that change only affects the local space-time. Then that ripple spreads out to nearby regions, which spread to regions farther out, until eventually the ripple reaches us. This theory of gravity is local because effects spread from place to place at the speed of light, instead of being instant. If the sun disappeared, that ripple would take about 8 minutes to reach us. Another observer might disagree about the length of the delay, but now we all agree that the sun disappeared first. There's no paradox. This is why nothing can go faster than light. The delay between cause and effect ensures all observers agree on the order of events. After Einstein fixed gravity, all of classical physics obeyed this important rule. Locality had been saved. Everything in the universe was connected by influences that travel at or below the speed of light. No paradoxes, no contradictions. The universe made sense. But then Einstein studied the new theory of quantum mechanics, and he made a terrible discovery. This revolutionary new theory violates locality. It requires faster-than-light influences, and almost nobody believed him. This brings us to one of the most famous photographs in physics. It was taken at the 1927 Solvay Conference, where the architects of the brand new quantum theory gathered to discuss their creation. Around 60% of the attendees would go on to win Nobel Prizes. This was the greatest assembly of physics minds ever gathered in one place. But Einstein thought they had gotten something fundamentally wrong, and this was his chance to prove it. So he took to the stage with a thought experiment designed to expose the fatal flaw in quantum mechanics. Imagine you fire a single electron through a narrow slit toward a circular detection screen. Quantum mechanics says that this electron has some sort of wave associated with it, called a wave function, which spreads out through space as it travels. When the electron hits the screen, you detect it at a single point. Where it turns up depends on the amplitude of the wave. If the wave is very big in a particular area, the electron is more likely to turn up there. Let's say it appears at one spot on the screen. So far, everyone in the audience was following. This is exactly what quantum mechanics predicts. Standard stuff. But then Einstein asked his next question, and it surprised them. Why doesn't the electron turn up at this other spot on the screen a moment later? There's only one electron, so we can't detect it twice. But the way quantum mechanics ensures this is deeply strange. When the electron was detected at the first spot, its wave function collapsed to zero everywhere else, instantly. That's why the probability of finding it at the second spot is now zero. There's no longer any wave there. The wave function has vanished everywhere except where the electron was detected. But Einstein asked the audience to really think about what this means. The measurement here must instantly affect the wave function over here, no matter how far apart these locations are. These spots on the screen could be centimeters apart, or meters, or light years. It doesn't matter. The collapse is instant everywhere. In other words, quantum mechanics requires instant influences across distance. It violates locality. It breaks the very rule that Einstein had worked so hard to establish with general relativity. Einstein concluded his talk by saying this is an entirely peculiar mechanism of action at a distance, and that this implies to my mind a contradiction with the postulate of relativity. Einstein's argument was so simple and his talk so short that people didn't know what to make of it. One audience member stood up and said, "I feel myself in a very difficult position because I don't understand what precisely is the point which Einstein wants to make. No doubt it is my fault." That man was Niels Bohr, the most influential figure in quantum physics at the time. Bohr's institute in Copenhagen had become the hub for the new field. Dozens of young scientists like Werner Heisenberg came to learn from him. As one of his disciples remembers, Bohr had invited a number of us to his home where we sat close to him, some literally at his feet on the floor, so as not to miss a word. Bohr wasn't the one who wrote the mathematical rules of quantum mechanics, but he told everyone what they meant. While others were confused by the theory, Bohr offered answers. His philosophy became known as the Copenhagen interpretation of quantum mechanics. Here's how it works. You have the wave function, which describes everything you can know about a particle or a system. It evolves according to the Schrödinger equation, and at some point you're going to make a measurement, and at that point, the wave function collapses. The wave function is all you can know about the particle. As Bohr would put it, it's wrong to think that the task of physics is to find out how nature is. The job of physics is just to predict measurements in the lab, which quantum mechanics does incredibly well. As for what the electron is doing when you're not looking, well, to Bohr, that question didn't even make sense to ask. The wave function tells you everything physics can or should tell you. Don't ask what's really happening. Just calculate the predictions and move on. Einstein couldn't stand the Copenhagen interpretation. In a letter to his ally Schrödinger, he called it a tranquilizing philosophy, or religion. Einstein felt his thought experiment exposed a critical weakness in the Copenhagen interpretation. He had shown that the way the wave function collapses is non-local, and so he reasoned, maybe the wave function is the problem. Maybe it's not the best way to describe the electron. After all, he may not have convinced Bohr during his talk, but he was determined to convince him during the rest of the conference. But here's where the story gets really interesting. Physicists tell a version of this story that you will find in physics textbooks and in popular science books, a story that physicists tell amongst themselves. What supposedly happened was that Einstein and Bohr had a great debate, and Einstein was unhappy with quantum mechanics because it was fundamentally probabilistic. He tried to show that there were conceivable experiments you could use to get around the uncertainty relations, and Bohr showed over and over and over again that you couldn't do that. And eventually, everybody agreed with Bohr. Einstein lost. Quantum mechanics won. End of story. But this version of history is wrong. We have documented evidence of this. In at least one case, Bohr completely misunderstood the purpose of Einstein's thought experiments. Einstein described a thought experiment that involved a box of photons and a mirror. Its purpose was to show the non-locality of the Copenhagen interpretation in action. But Bohr just misunderstood it. When he recounted it to others later on, he drew a little diagram of what Einstein's thought experiment setup was, and the diagram didn't have the mirror in it at all. He had completely missed the point. And yet this is taken as the great victory for Bohr over Einstein, which is crazy. But history is written by the victors. To understand what Einstein was really arguing for, think of the relationship between Newton's gravity and general relativity. Newton's theory works well in most situations, but in that theory, gravity is a non-local force, leading to paradoxes. This was the motivation for coming up with Einstein's general relativity, which is local. Einstein believed the same logic applied to quantum mechanics. His thought experiment revealed that quantum theory is non-local. So, just like with Newton's gravity, quantum mechanics must not be the final theory. There must be a local theory that will replace it. And, as a bonus, he thought this new theory might even unify gravity with the quantum world. It would be the ultimate theory of everything. But Einstein hadn't even persuaded Bohr that quantum mechanics really is non-local. So, in 1935, he made one last attempt to convince the community that there was a contradiction between quantum mechanics and relativity. With the help of two younger colleagues, Boris Podolsky and Nathan Rosen, he formulated another, even more striking thought experiment that shows the non-locality of quantum mechanics. This paper is now known as the EPR paper, named after its three authors, and this thought experiment would change physics forever. Here is a simplified version of their thought experiment. Imagine a single high-energy photon suddenly becomes two particles. One of them is an electron, and to conserve total charge, the other is a positron. One is negative, one is positive, they cancel out. But both electrons and positrons have a property called spin. And like electric charge, this also needs to be conserved. If the light started out with zero spin, then the two particles together must have zero total spin as well. For example, if the direction of the electron spin is pointing up, the positron has to have spin pointing down so that they perfectly cancel out. But the electron spin could have been pointing left instead, or right, or any direction. All of these possibilities are valid. So the rules of quantum mechanics say that the electron does all of these possible things at once until it's measured. It's not just that we don't know what the spin is. The electron really is doing everything simultaneously. It exists in what's called a superposition of all possible spin directions. The only restriction is that whatever the electron is doing, the positron must do the exact opposite. This also means that when the electron is measured and its state is determined, so is the positron's. This is what we mean by entanglement. The two particles' states depend on each other. They're connected. But how do we measure the particles and force them to do one thing? For that, we use something called the Stern-Gerlach machine. It's essentially a strangely shaped magnet, and it's how we measure spin. The orientation of the magnets determines what axis you're measuring the spin along. For example, if the machine is oriented vertically and we shoot in a particle with spin in the positive z direction, it will certainly go to the spot we'll call plus. If instead a particle has negative z spin, it will certainly go down to the spot we'll call minus. So this Stern-Gerlach machine measures spin along the z-axis. It sorts particles into two categories, plus and minus. So what happens when we put in one of our entangled particles? When the electron goes into this machine, it either goes to plus or to minus with 50-50 probability. Let's say our electron goes to plus. This means it went from being in an indeterminate state, doing all possible things at once, to having a definite positive z-spin. But what about the positron? Well, the only way to conserve spin is if it's now in the negative z-spin state. When it's measured, there is a 100% chance it goes to minus. It has to be that way to conserve spin. The total spin must remain zero. But the authors of the EPR paper realized there's something very odd about this result. To see what's wrong, let's imagine that the electron and the positron carry these envelopes with them. These envelopes represent the state of the two particles. Until they're measured, both particles are in a superposition of being plus and minus at the same time. So both options are in the envelope. But now let's move the positron far, far away to someone on the other side of the galaxy. In this analogy, opening the envelope is like measuring the spin of the electron. That causes the wave function of the electron to collapse to just one possibility. In this case, it's plus. But what happens to the other envelope, far away across the galaxy? Well, it needs to instantly collapse to minus. Otherwise, when the experimenter opens their envelope, they would have a chance of seeing plus, which would violate the conservation of spin. The two particles can't both be plus. But if the distant envelope needs to collapse instantly when the electron is measured, then how does it know what to collapse to? It must receive information from the faraway electron. But that message has to travel much faster than the speed of light to get to the positron in time. And so, with this argument, Einstein, Podolsky, and Rosen had shown that the Copenhagen interpretation of quantum mechanics really is non-local. Einstein had already shown this in his conference talk 8 years earlier, but this argument was even more decisive. It was clearer, more vivid, impossible to misunderstand. It does seem like the same basic idea, but now it's ramped up. You've got these two separate particles, two separate measurements, and one measurement influencing the other measurement definitely feels wrong. Einstein realized that it's measurements that are the problem in quantum mechanics. The act of measurement is what forces the non-locality. The wave function of a single particle, or of this pair of particles, can end up spread over vast distances. That isn't itself an issue. Waves can be big. But when the wave function collapses, the information about that collapse needs to spread everywhere instantly. The wave function is everywhere, so collapsing it requires faster than light communication. That's what makes quantum mechanics non-local. But the EPR paper didn't just point out this non-locality issue. They proved that there is only one local alternative theory for explaining this experiment. In this local story, instead of the electron choosing whether to be plus or minus when it's measured, it actually makes that choice earlier, when it's still in contact with the positron. There's some random process that puts plus or minus into these two envelopes while the particles are still together. These predetermined values are called hidden variables because they're hidden from our view until we measure. And because this alternative theory assigns these hidden variables in a local way, while the particles are still in contact with each other rather than over a big distance, we call this a local hidden variable theory. This local hidden variable theory is going to be able to explain this experiment really simply. Let's send the positron far away. Now, when the electron is measured as plus, it doesn't have to rush to tell the positron. The positron already knows. The decision was made long ago when they were still together. There is no action at a distance. This local hidden variable story is so much more sensible than the quantum one. It's elegant. It's intuitive. It respects the speed limit of the universe. So we're forced to accept one of two explanations for this experiment. Either non-locality, like the Copenhagen interpretation of quantum mechanics, or a local hidden variable theory. Given that non-local action at a distance contradicts relativity, Einstein thought this was definitive proof that the Copenhagen interpretation of quantum mechanics is wrong. Therefore, there must be some local hidden variable theory that will replace it. Quantum mechanics is incomplete. It's not the final word. Nature must have a better, more sensible way of doing things that we just haven't discovered yet. Einstein showed us that quantum mechanics allows influences that seem to travel faster than light. He believed this was proof that quantum mechanics needed to be replaced, but he died before anyone could test whether he was right. The EPR paper certainly got a lot of attention, though not in the way Einstein had hoped. Without asking Einstein for permission, Podolsky leaked the paper to the press, and the story ended up in the New York Times. Einstein was the most famous scientist in the world, and he was going after the strange but wildly successful theory of quantum mechanics. Of course, the press loved it. Headlines proclaimed that Einstein had found a flaw in quantum theory. The public was fascinated. But what did scientists actually think of the argument itself? What did the physics community make of Einstein's most careful, most devastating critique of quantum mechanics? The reaction of the physics community was at first mixed. There were some people, sort of old allies of Einstein's, who were very happy with it. Schrödinger was at the top of that list. In fact, in an attempt to clear up some of the misunderstandings that people were having about the EPR paper, Schrödinger published his own thought experiment to back up Einstein and show the kind of problem that he and Einstein had with quantum physics. That thought experiment became known as Schrödinger's cat. Meanwhile, Bohr's reaction was very different. It was something like, "Oh my God, what? What the hell is this? He must be wrong. How do we show that he's wrong?" Bohr, ultimately, in his sort of painful and complicated style, ended up coming up with a response to the EPR paper. This response is famously obscure and difficult to understand. People have read it carefully, analyzed it in detail, and the conclusion is that Bohr's reply is either nonsensical or makes some actual mistakes. There is a very well-turned sentence which Bohr took a great deal of trouble in formulating, and yet its meaning is absolutely obscure. Bohr said in his reply to EPR, in his multiple replies actually, that there is no question of anything non-local going on. According to Bohr, Einstein had simply misunderstood quantum mechanics. There was no problem, no contradiction, no faster than light influences. The ultimate reaction of the physics community, at least in the immediate years and decades following the publication of EPR and Bohr's reply in 1935, was to think that Bohr had settled it with his response, even though people didn't really understand what Bohr had said. This is remarkable when you think about it. The physics community decided that Bohr had won the debate based on a reply that nobody could understand. But Bohr was so influential, so revered, that his authority alone was enough. If Bohr said Einstein was wrong, then Einstein must be wrong. Never mind that Bohr's explanation made no sense. Never mind that he seemed to have missed Einstein's point entirely. Bohr had spoken, and that was that. 2 decades later, Einstein died, still questioning quantum mechanics. But the majority of the physics community had moved on without him. They had accepted the Copenhagen interpretation. They had accepted that quantum mechanics was correct and complete. They believed Einstein had simply been unable to accept the new physics, that he had grown old and stubborn and out of touch. But Bohr never forgot about the EPR paper. It had clearly bothered him deeply. In 1962, 7 years after Einstein's death, Bohr gave an interview about Einstein, and he lamented that Einstein wasted decades on fruitless thought experiments because he simply could not accept quantum mechanics. Bohr said in that interview, it was terrible that Einstein fell in that trap to work with Podolsky. Rosen is worse, from my point of view. Rosen, even today, believes the EPR thought experiment. Podolsky has given it up, as far as I know. The whole idea is absolutely nothing. When one really gets into it, you may think that I say it too strongly, but it is true. There's absolutely no problem in it. Those were among Bohr's final words on the subject. The next day, Bohr took a nap after lunch and never woke up. And so, after many decades, the Einstein-Bohr debate was over. Bohr had won by sheer force of personality and authority. Einstein's concerns about locality were dismissed, forgotten, relegated to history. Bohr's authority was part of the reason the EPR paper didn't get the attention it deserved. But there was another reason physicists ignored it, perhaps an even more important reason. In the EPR experiment, both theories, the Copenhagen quantum mechanics and Einstein's local hidden variable alternative, make exactly the same prediction. You get the same results either way. No matter which theory is correct, when you measure the electron as plus, you always find the positron to be minus. The predictions are identical. Debating 2 different interpretations of the same experimental result seemed like armchair philosophy, not real physics. It seemed like a waste of time. The Copenhagen interpretation makes good predictions, incredibly good predictions. It's the most successful theory in the history of science. So why not just teach that and move on? Why waste time on these philosophical questions that can never be answered? The message that kind of got pushed was shut up and calculate. Just use the equations. Don't ask what they mean. The general attitude was, this is done, who cares, none of this matters. It's all settled. Einstein and Bohr had a big debate about it, and Bohr won. And if you disagreed, people would ask, do you think you're smarter than Niels Bohr? Do you think you're smarter than Albert Einstein? The implication was clear. If these 2 giants couldn't resolve it, what hope did anyone else have? Just shut up and calculate. It seemed like it would be impossible to resolve this debate. The 2 theories made the same predictions, so how could you ever test which one was right? How could you turn this philosophical debate into real experimental physics? It seemed hopeless. Until another physicist turned his attention to it. His name was John Bell, and he would change everything. John Bell was an undergraduate student shortly after World War II in this new era of physics. And so, of course, he was taught the Copenhagen interpretation. That was the standard view, the orthodox interpretation that every physics student learned. But John Bell's doubts about quantum mechanics, by his own recollection, showed up basically the minute he learned it. In his first quantum mechanics class, he was getting pretty upset with the instructors and saying, "You're being too vague. What the heck do you mean about measurement? When does a measurement happen? What counts as a measurement? Why does the wave function collapse when we measure, but not at other times?" His professors couldn't give him satisfactory answers. Bell was never fully satisfied by the answers he got about the foundations of quantum mechanics. But when he was doing his PhD, he was encouraged to study something a little bit more respectable. questioning the foundations of quantum mechanics was not a good career move. It was considered philosophy, not physics. So he studied nuclear physics and went on to have a very accomplished career at CERN, the European Organization for Nuclear Research. He became an expert in particle physics and accelerator design. He was a successful, respected physicist doing important work. But after 8 years of working in particle physics, in 1963, he took an academic sabbatical. And finally, he had time to focus on his doubts about quantum mechanics. He said later, "I always knew that it was waiting for me." For 8 years, he had pushed these questions to the back of his mind, but they had never gone away. Now he finally had the time to think about them properly. He began by re-examining the old debates and the papers that most physicists had long since dismissed as philosophical distractions. He read Einstein's papers. He read Bohr's replies. He read the EPR paper carefully, multiple times. After this research, he said, "I felt that Einstein's intellectual superiority over Bohr, in this instance, was enormous. A vast gulf between the man who saw clearly what was needed and the obscurantist." Bell realized that Einstein's logic was sound. Einstein had been right all along. One of the two conclusions must be true. Either quantum mechanics is non-local, or there's a local hidden variable theory that will replace it. The question was, could you prove which one using an experiment? Could you turn this philosophical debate into testable physics? An experiment of this sort seemed much more feasible by Bell's time. The EPR paper was the first to consider the idea of entanglement. These days, entanglement is a core feature of quantum mechanics. Scientists create entangled particles in laboratories all over the world. But Einstein had been first to even point out that entanglement existed. This is why the EPR paper was set up as a thought experiment, because no one had made such an exotic state of matter in 1935. The technology didn't exist. But in the intervening decades between Einstein's work and Bell's, between 1935 and 1964, entanglement had become a serious topic of study. By Bell's time, there were reliable ways to make it in the lab. In fact, a physicist named Madame Wu had famously reproduced the EPR thought experiment as a real experiment. She had actually created entangled particles and measured them. But simply doing the EPR experiment in real life isn't enough to tell you which explanation is correct, since both theories predict the same thing. You measure one particle and find the other has the opposite value. That happens whether quantum mechanics is right or whether local hidden variables are right. The experiment can't distinguish between them. But Bell wondered if there was another version of the experiment, a modification, a twist, where the non-local and local theories would have to give different results, where they would make different predictions that you could actually test. If you're asking that question and you're playing with the EPR setup, then it's literally, not just figuratively, a twist. Bell realized you could rotate the measuring devices. Here's Bell's brilliant modification of the EPR experiment. Make your entangled electron and positron again, just like in the original EPR setup. But now, instead of just measuring them with a Stern-Gerlach machine oriented one way, the experimenters get a choice about how to orient their machine. They can rotate it. The three different choices are 0 degrees, 120 degrees, and 240 degrees. Three different angles, evenly spaced around a circle. This is the twist on the EPR experiment. The experimenters get to choose independently which angle to use, so the electron might be measured at 0 degrees, while the positron is measured at 240 degrees. Different angles, chosen independently, measured simultaneously on entangled particles far apart. If both experimenters happen to choose the same axis, then we know what happens. They have to get the opposite result from each other to conserve spin. That's just like the original EPR experiment. Nothing new there. The interesting case is when the experimenters happen to choose different axes. different angles of measurement. The number we want to predict here is the disagreement rate. The probability that the electron's result is different from the positron's result when they're measured at different angles. This is the key number. This is what will be different between the two theories. At first, let's see what quantum mechanics predicts for this number. Let's say the electron is measured with the 0-degree axis and comes out as plus. Now that its spin has collapsed to positive z, the positron spin needs to instantly collapse to be negative zaz. This is the non-local part of quantum mechanics. The wave function collapses everywhere at once, faster than light. But what happens when this positron is measured by a machine tilted at 120 degrees? Well, the positron's spin is already pointing mostly downward, but now it's being measured along an axis that's tilted. The positron spin is already almost facing the plus end of the tilted machine, so it's much more likely to go to plus than to minus. In fact, you can calculate exactly how likely. There's a 75% chance it goes to plus and only a 25% chance it goes to minus. So the disagreement rate is 25%. 1/4 of the time, they get different results. And you can show that for any two different axes the experimenters select, the geometry is analogous. They all have this same disagreement rate of 25%. Anytime the experimenters choose different axes, different angles of measurement, they will get the same outcomes 75% of the time, and different outcomes 25% of the time. That's the prediction of quantum mechanics. 25% disagreement when measuring at different angles. Now, let's consider the local hidden variable alternative theory. Remember, in this theory, the particles decided their spins in advance when they were still together. The particles are on a mission. Their aim is to make you believe that they're acting according to quantum mechanics when really they're acting locally. Now, we are anthropomorphizing particles here, but it's really useful to imagine them this way. We're trying to figure out if it's always possible for them to use a hidden variable theory to get the same experimental outcomes as Copenhagen quantum mechanics, or if in this new situation, our scheming particles won't be able to fool us. You can think of it like this. Each of the particles is going to be asked one of three possible questions. The three angles: 0 degrees, 120 degrees, or 240 degrees, and they need to decide on their answers while they're still together, so that they can coordinate on their strategy. When they're done figuring out a plan for how they would answer any of the three questions, they pack away those hidden variables, those predetermined answers, into 3 sealed envelopes for each particle. 1 envelope for each possible angle of measurement. The question is, what strategy should our sneaky particles take to make people believe that they're following quantum mechanics? Remember, quantum mechanics predicted a disagreement rate of 25%. So our particles want to match that. Whenever they happen to be asked different questions, measured at different angles, their answers need to disagree about 25% of the time. That's the goal. Can they do it using only local hidden variables, only predetermined answers decided in advance? So, what's the best strategy? Well, there's actually only 2 basic things that they really can do. The first strategy is this. The electron answers the same way for each of its 3 axes, all 3 angles, and the positron answers in the opposite way for all 3 angles. Let's say the electron's 3 envelopes all say minus, 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 and the positron's 3 envelopes all say plus, plus, plus. Simple enough. But this is a terrible idea. This strategy fails immediately. Because whatever 2 different axes the experimenters happen to choose, whatever 2 angles they measure, the disagreement rate is 100%. They always disagree. The electron always says minus, the positron always says plus. That's very different from the 25% disagreement that quantum mechanics predicts. so that strategy doesn't work at all. But there's only one other basic strategy that the particles could use. Instead of the electron doing exactly the same thing for all three axes, it does the same thing for any two of its axes, and then something different for the last one. For example, maybe the electron's envelopes say plus, plus, minus. Two pluses and one minus. And then the positron does the opposite. So its envelopes say minus, minus, plus. This is just one example of this type of strategy, but it turns out that for all possible strategies like this, for all possible ways of arranging two of one answer and one of another, the disagreement rate is going to come out the same. Let's calculate it. Let's imagine first that the experimenter who's measuring the electron happens to measure it along the 120-degree axis. That's the second angle, and the electron's envelope says plus for that angle. They make this choice 1/3 of the time, since there are three possible angles to choose from. Now, to calculate the disagreement rate, we need to see what happens when the experimenter who's measuring the positron happens to measure a different axis from this one, a different angle. So, one of the other two angles, either 0 degrees or 240 degrees. But look at the positron's envelopes. In either one of these cases, at either of these other angles, the positron is also plus. And so the two answers agree with each other. They're both plus. And so the answers have no disagreement. We can multiply this by 0 for the disagreement contribution. But 2/3 of the time, the experimenter measuring the electron will happen to measure it at one of the other two axes, one of the other two angles. Let's say the 0-degree axis, where the electron's envelope says plus. Now, the experimenter measuring the positron will measure at one of the two other angles. But you can see that only one of those two positron envelopes disagrees with the electron's answer. One says minus, which disagrees, and one says plus, which agrees. So they only pick an axis that disagrees half of the time. So the disagreement rate for this case is 2/3. The probability the electron is measured at one of its first two angles, times 1/2. The probability the positron is then measured at an angle that disagrees. 2/3 times 1/2 equals 1/3. That's roughly 33%. When our scheming local particles are interrogated, when their predetermined answers are checked, their answers for different questions match just a little too often. They agree more often than quantum mechanics says they should. They simply can't fake the results of Copenhagen quantum mechanics. No matter what strategy they use, no matter how they arrange their predetermined answers, they can't get the disagreement rate down to 25%. The best they can do is 33%. Local hidden variables predict at least 33% disagreement. Quantum mechanics predicts exactly 25% disagreement. So, Bell's proof showed that non-local and local theories make different predictions about how often the two results will disagree when the experimenters measure different axes, different angles. Non-local quantum mechanics predicts disagreement only 25% of the time. Local hidden variables predict disagreement at least 33% of the time. These are different numbers, different predictions, and that means you can actually test which theory is correct. After 30 years of people saying this was just philosophy, Bell had shown it was physics. Real, testable, experimental physics. So to find out if there really is a local hidden variable theory, you just need to do the experiment. You need to create entangled particles, measure them at different angles, and count how often you get different results. If you get different results 25% of the time, quantum mechanics is right and the universe is non-local. If you get different results 33% of the time or more, then local hidden variables are right, and Einstein's dream is alive. One number, one experiment. The answer to one of the deepest questions in all of physics. Bell published his theorem in 1964, and it was largely ignored at first. Most physicists still thought this was philosophy, not worth their time. But a few people recognized its importance. A few people realized that Bell had done something extraordinary. He had taken a philosophical debate and turned it into an experimental test. He had made the invisible visible, the untestable testable. And slowly, very slowly, people began to take notice. Experimentalists began to think about how they might actually perform this test, how they might actually answer Einstein's question once and for all. It would take another decade before the technology was good enough to really do it properly. But in the 1970s, a physicist named Alain Aspect performed a series of experiments that would finally put Bell's theorem to the test. These experiments were extremely challenging. The equipment was crude by today's standards. Creating reliable entangled particles was difficult. Measuring them at different angles quickly and accurately was difficult. Everything was difficult. But Aspect and his team persevered. They spent years perfecting their technique, calibrating their equipment, eliminating sources of error. And then, finally, they were ready. They would create pairs of entangled photons, particles of light, and measure them at different angles, just as Bell had described. They would count how often the measurements disagreed, and that single number would tell them whether Einstein or Bohr had been right, whether the universe respects locality or violates it, whether quantum mechanics is the final theory or just a stepping stone to something deeper. Everything hung on this one measurement. 4 decades after the EPR paper, 3 decades after Einstein's death, the answer was finally within reach. Welcome to the Institut d'Optique in France. You are here in the place where Alain Aspect performed 40 years ago his experiments on the measurement of Bell's inequalities. Here are some of the original pictures of this experiment, which was much more challenging than it is today. It was a real experimental tour de force. This is one of the original pieces of equipment from that experiment, one of the polarizers. It looks simple now, sitting on this small breadboard, but at the time it represented the cutting edge of experimental physics. Let me show you how we do this experiment today with modern equipment. This is our main source, and this beam is directed towards this element, which is the key element of the setup. It's a pair of crystals that produces pairs of entangled photons. We will produce a pair of entangled photons, and both are propagating along each of these 2 arms. They're separated, sent in different directions. So here we have the 2 detection arms, and we can rotate the half-wave plate to change the orientation of the measurement basis. We can choose what angle to measure at, just like Bell described. The experiment that we did with light was a little bit different from the one we described earlier with electrons and positrons, so let me explain how they correspond. Here's a diagram of the photon experiment. First, we have this element that makes the entangled pair of particles. Then, the entangled particles go off on separate arms of the experiment, traveling in different directions toward 2 different detectors. In our previous thought experiment with electrons, we could decide the direction that we're going to measure the particles in by rotating the Stern-Gerlach machines. And in this experiment with photons, it's actually really similar. We have these 2 polarizers that we're able to rotate independently, and that is going to decide which direction these particles are measured in. The polarizers for photons work just like the Stern-Gerlach machines for electrons. And so this experiment with light is completely equivalent to Bell's experiment. Same physics, same test, just different particles. Bell expected that the experiments would show that the predictions of quantum mechanics were correct, and that there was some kind of non-locality in nature. Before the first Bell test was done, John Bell said, in view of the general success of quantum mechanics, it's very hard for me to doubt the outcome of such experiments. He didn't expect quantum physics to be wrong because who would bet against quantum mechanics? You'd have to be crazy. Quantum mechanics had been tested thousands of times and had never failed. It was the most successful theory in the history of science. But now, for the first time, there was a test that could genuinely prove whether one of its fundamental features, one of its strangest predictions, was really true. Remember, the two different outcomes for Bell's theorem depend on how often two different measurement axes are going to have results that disagree with each other. How often do you get different answers when you measure at different angles? Here's how we measure that disagreement rate. First, we're going to start with both of the measurements being in the same direction, the same angle. And now we expect that these two photons are always going to disagree with each other, because they have opposite polarizations. They're entangled in such a way that they must give opposite answers. We're going to create a bunch of entangled particles and find out how many of them disagree with each other per second. This is going to give us a measure of the total number of particles coming per second. That's because this device is making loads and loads of entangled particles continuously. And so we just need to know how many of them are arriving at our detectors at a time. This gives us our baseline, our reference point. Then we rotate one of the axes, one of the polarizers. We change the angle of measurement on one side. And now we measure the number of disagreeing pairs per second with this new configuration. And then, dividing these two numbers will give us the disagreement rate, the fraction of particle pairs that give different results when measured at different angles. And remember, quantum mechanics predicts that the disagreement rate will only be 1/4, 25%, whereas local hidden variables expect this number to be 1/3, 33% or higher. This is the moment of truth. Let me show you the actual measurement. So, I started at 2,000 counts per second when both detectors were aligned. And now I have rotated one polarizer, and the count rate dropped to 500. So that's basically perfect. That really works pretty well. The disagreement rate is 500 divided by 2,000, which equals 1/4, exactly 25%. We did do this experiment again and again, and the number we got very much agreed with quantum mechanics every single time. 25% disagreement, not 33%, not anything close to 33%, 25%, exactly as quantum mechanics predicted. Local hidden variables had failed. Einstein's dream of a local theory had failed. The universe really does violate locality. Quantum mechanics really does involve faster-than-light influences. This should have been one of the most shocking discoveries in the history of physics. But instead, it became one of the most misunderstood. You'll find in all sorts of physics textbooks and papers and whatnot that what Bell's theorem proves is that it rules out local hidden variables, or local realism. That's what most people think it means. That's what most physicists will tell you. But John Bell himself said that was an error. He said it's really quite remarkable how many people make that error. People constantly misunderstand what his theorem actually proved. I always get confused at the conclusion of Bell's theorem, because there's a lot of people who say, okay, it rules out hidden variables, or things have to be non-local, or whatever. But what do you actually think it proves? Yeah, I think it is super confusing, and when I first learned Bell's theorem, I was told that it rules out local hidden variables. That's the standard story. That's what's in the textbooks. But I've heard this other argument that it sort of disproves either locality or realism, that you have to give up one or the other. If you say, okay, it means that you give up local realism, and so that means you somehow have a choice between giving up locality and giving up realism. But if you're giving up realism about what? Like, you've got to tell me what you mean by realism, because for most definitions of that word, you'd also be giving up locality anyway. So what the hell are you saving? I just don't understand. It's a really deep misunderstanding that shows up in almost every single textbook on the subject. So what does Bell's theorem really prove? Let's go through the logic carefully, step by step. Start by assuming locality for the entangled particles. Assume that nothing can travel faster than light, that there are no instantaneous influences across space. Given that assumption, using the EPR argument, the only way for the particles to coordinate their outcomes is using local hidden variables. They have to decide their answers in advance while they're still together. That's the only local way to explain the correlations. Then, Bell's proof showed that local hidden variables predict an incorrect experimental result. They predict at least 33% disagreement, but the experiment shows 25% disagreement. The prediction is wrong. Therefore, the assumption of locality must have been wrong. That's the logic. That's what Bell's theorem actually proves. We are obliged to invoke something like actions going faster than light from one place to another. Faster than light influences are real. They exist in nature. The EPR paper by itself had shown that the Copenhagen interpretation is non-local, which is why Einstein thought there must be an alternative way to describe the experiment that is local. But Bell's theorem says that's not true. There is no local alternative. Any theory that correctly describes this experiment must be non-local. It must involve faster-than-light influences in some form. But I still would hesitate to say that that means that Einstein was wrong, right? Because what I would say is, this shows that Einstein was right to be concerned about all of this. People often claim that Einstein's problem was that he simply couldn't accept quantum mechanics, that he was stubborn, that he was old and out of touch. But it was only because he refused to shut up and calculate that he discovered two of the most important aspects of quantum mechanics: entanglement and non-locality. Einstein was the first person to realize that entanglement even existed. He was the first to point out that quantum mechanics involves non-locality. These are now considered fundamental features of quantum theory, and Einstein discovered them. The heart of the debate between Einstein and Bohr was about whether there was a problem, whether there was something to be concerned about. And the major concern that Einstein brought to the table from the beginning was about locality. But you know what Bell showed? Oh, yeah, all that stuff that Einstein was concerned about locality, he was completely right to be worried about it. We have a problem. Einstein had identified a genuine, deep issue with quantum mechanics. He was right that the theory has this bizarre non-local feature. He was right that this seems to contradict relativity. He was right that this deserved serious attention. Where Einstein was wrong was in thinking that this meant quantum mechanics must be replaced. It turns out quantum mechanics is correct, but Einstein's concerns were completely valid. If these particles really are acting non-locally, if influences really can travel faster than light, this should cause paradoxes, shouldn't it? This should break the universe. This should create all the same problems that instant gravity had. The problems that Einstein spent 10 years fixing with general relativity. Well, it does cause paradoxes, but the paradox seems to be surprisingly tame, surprisingly manageable. Let me show you what I mean. Imagine you and your friend are measuring a pair of entangled particles. You're far apart, maybe on opposite sides of a laboratory, or opposite sides of a planet, or even opposite sides of a galaxy. Suppose an observer sees you measure your particle first, and then your friend measures hers a moment later. That observer thinks that you collapsed the overall state of both particles with your measurement, and your friend just found out the result when she measured hers. Your measurement was the cause, and her measurement revealed the effect. But here's the problem. Another observer will see the situation in reverse. They're moving at a different speed, so they have a different perspective on time. They see her measure first, and then you measure. To them, it was her measurement that caused the collapse, not yours. Her measurement was the cause, and yours revealed the effect. But who's right? Which measurement was the cause of the collapse, and which was the effect? It seems to depend on your frame of reference, your speed, your perspective. This is exactly the kind of paradox that Einstein was worried about. different observers disagree about which event happened first, which was cause and which was effect. This paradox is worrying, but it isn't as bad as the usual faster-than-light paradoxes. In relativity, if you can communicate faster than light, then you can exploit how different observers disagree about timing to send messages backward in time. Here's how that would work. If your friend who's on a rocket sends you an instant message, and you send an instant message back, then, in some frames of reference, your message can arrive before she even sent the first one. If your message says, "Don't send your original message," and so she doesn't, then you've got yourself a paradox. A genuine, logical impossibility. What prompted you to send this message if she never sent you anything in the first place? You sent a message telling her not to send a message, which means you never would have sent your message, which means she would have sent her message, and so on forever. It's a causal loop, a contradiction, an impossibility. Quantum mechanics sidesteps these catastrophic paradoxes through a fundamental constraint, a built-in protection mechanism. The outcomes are random, so you can't send messages faster than light. When you measure your particle, you get a plus or a minus completely at random. 50-50 chance. You have no control over the outcome. Your friend measuring her particle also gets a random result. Now, the results will be correlated, they'll be connected, but they're still completely random. So, there's no way to send any faster-than-light message in this way. You can't encode information in random outcomes that you can't control. That's what prevents us from sending messages back in time using quantum mechanics. That's the loophole that saves the universe from paradox. So, quantum mechanics is non-local. It does involve faster-than-light influences, but it doesn't lead to the sort of catastrophic paradoxes you might expect from relativity. It's an uneasy truce. Quantum mechanics may not break the letter of relativity's laws, but it certainly violates the spirit. It respects the cosmic speed limit for sending information, for sending messages, but it violates the deeper principle that everything should be local, that influences should propagate from place to place rather than jumping across space instantly. And non-locality isn't the only troubling thing about quantum mechanics. The Copenhagen interpretation still doesn't explain what an electron is really doing, what it really is, and why it acts so differently when measured. Why does measurement cause the wave function to collapse? What is a measurement? When does it count as a measurement? These questions remain unanswered. Despite this, many physicists took Bell's theorem to mean that the Copenhagen interpretation was right all along. They thought Bell had proven that there's no alternative, that we're stuck with wave function collapse and all its mysteries. Einstein was wrong, Bohr was right, case closed. But Bell himself rejected this conclusion completely. He spent the rest of his life championing alternative interpretations of quantum mechanics, including a hidden variable interpretation called pilot wave theory or Bohmian mechanics, named after physicist David Bohm, who developed it in the 1950s. Bell's theorem doesn't rule this interpretation out because the pilot wave theory is non-local, just like the Copenhagen interpretation. It has faster-than-light influences built into it explicitly. But unlike Copenhagen, pilot wave theory actually explains what the electron is doing. It says the electron is always a particle with a definite position, guided by a wave that really exists and influences its motion. The wave is non-local, it connects distant particles, but at least you have a picture of what's happening. It was Bell's theorem, and Bell's subsequent tireless work promoting alternatives to Copenhagen that made studying the meaning of quantum mechanics respectable again. He showed that mere armchair philosophy and thought experiments can have real consequences in physics. He showed that asking what quantum mechanics means, what it's really telling us about reality, is not a waste of time. It's real physics, important physics. We need to be teaching quantum physics in a different way. We need to be teaching Bell's theorem in a different way. We do often teach Bell's theorem to physics students, and it's taught as something that rules out local hidden variables and nothing more. But that's just not true. That's not what it proves. Bell's theorem says that quantum physics is in very serious tension with relativity on the issue of locality. That's the real message. That's what students should learn. Quantum mechanics and relativity, the two pillars of modern physics, are in conflict. They can't both be completely right in their current forms. Something has to give. Either our understanding of quantum mechanics is incomplete, or our understanding of relativity is incomplete, or both. This is one of the deepest unresolved problems in all of physics, and it stems directly from Bell's theorem. But most physicists don't know this because they were taught the wrong lesson. John Bell passed away suddenly at the age of 62 in 1990. He didn't know it, but he had been nominated for the Nobel Prize just a year earlier. The nomination came too late. He died of a stroke, gone far too soon before he could receive the recognition he deserved. In a talk he gave in Geneva in January 1990, just 8 months before he died, he said, "I think you're stuck with the non-locality. I don't know any conception of locality which works with quantum mechanics." That was pretty much his last word on the subject. His final message to the physics community. Non-locality is real, it's unavoidable, we have to deal with it. And so that's it. There really are faster-than-light influences in the universe. Bell's theorem proves it. The experiments confirm it. Quantum entanglement connects particles across vast distances, and when you measure one, the other responds instantly, no matter how far away it is. The universe violates Einstein's cosmic speed limit. Locality is dead. But maybe, just maybe, there is a way out. Maybe there's one more escape hatch that we haven't considered yet. Maybe there is another way to interpret quantum mechanics that's even more bizarre than the Copenhagen interpretation, even more radical than anything Bohr or Einstein ever imagined. An interpretation so strange that most physicists rejected it when it was first proposed. But an interpretation that might, just might, save locality after all. Imagine the EPR thought experiment again. We can think of the entangled state as being in a superposition, the electron being up and the positron being down, and simultaneously the electron being down and the positron being up. Both possibilities existing at once, overlapping, interfering. In the Copenhagen interpretation, when you measure a particle and you get only one result, say plus, the other part of the superposition collapses. It vanishes. It ceases to exist. You started with two possibilities, and measurement destroys one of them, leaving only the result you observed. This collapse happens instantly everywhere, which is why Copenhagen is non-local. But in our examples, we've seen that measurement collapse seems to be the source of non-locality. The collapse is what requires faster-than-light influences. The collapse is the problem. So why don't we just get rid of collapse altogether? Why don't we just say that collapse never happens? This is what the many worlds interpretation of quantum mechanics proposes. It's a radical idea, first suggested by physicist Hugh Everett in 1957 and later developed and championed by others. The idea is simple but profoundly strange. When you measure a particle, instead of you collapsing the particle to one outcome, both outcomes happen. Both possibilities remain real. And there are two parallel versions of you who see each outcome. You have become entangled with your particle because your state depends on what the particle is doing. One version of you sees plus, another version sees minus, and both versions are equally real. Both exist. Both continue on into the future, completely unaware of each other. You've split into two parallel versions, two branches of reality. It sounds insane. It sounds like science fiction. But there's one huge benefit of this interpretation. one enormous advantage that makes some physicists take it seriously. When your friend far away is about to measure her electron, your positron doesn't need to rush to tell the electron what the answer will be. There's no faster than light communication required. Why not? Because there are already two versions of the electron, existing in superposition. One version is plus, one version is minus, and they contain the right answer for each version of your friend. When she measures, she splits into two versions as well. One version of her measures plus and sees the version of the electron that's plus. The other version of her measures minus and sees the version that's minus. Everything matches up perfectly without any need for faster-than-light influences. There was no need for instant communication to explain the EPR experiment. The correlations are explained by the branching of reality, not by signals traveling faster than light. But how is that possible? Doesn't Bell's theorem prove that the two particles must communicate faster than light? Doesn't it prove that non-locality is unavoidable? Well, here's the subtle point. In Bell's proof, we assumed that all measurements have just one outcome. We assumed that when you measure plus, that's the only thing that happens. But that assumption just isn't true in many worlds. In many worlds, both outcomes happen. The measurement has two results, not one. And this means that, technically, Bell's proof doesn't even apply in the many worlds case. The assumption that Bell used to derive his theorem is violated by many worlds. So is many worlds local? The answer is complicated. In one sense, no, because just like in Copenhagen quantum mechanics, entangled pairs can be separated by a huge distance and still share their state. The wave function still connects them across space. But many worlds is local, unlike Copenhagen, in the sense that these faraway entangled particles do not influence each other faster than light. There's no collapse, no instant jump from superposition to a single outcome. Everything evolves smoothly according to the Schrödinger equation, which is completely local. Information propagates at or below the speed of light. Many worlds obeys Einstein's universal speed limit, the one he worked so hard to establish. But is it really worth accepting that there are many versions of you in parallel universes just to recover locality? Is saving Einstein's principle of locality worth such an extravagant price? Well, locality isn't the only reason many worlds has become more and more popular among physicists. There are other reasons, deeper reasons, why some find it more compelling than the Copenhagen interpretation. I also really like many worlds, because Copenhagen never sits right with me. When you start telling the story of what happens at measurement, it's like, well, what is a measurement? When you have this quantum system and there's some other system which is much larger, like a measuring device, and so, but it always feels a little bit arbitrary. Where do you draw the line between the quantum system and the classical measuring device? When exactly does the collapse happen? Whereas this argument that every time two quantum particles are interacting, their wave functions are essentially combining and becoming entangled, that to me feels more consistent. It feels like one unified story instead of two separate sets of rules. You don't need one set of rules for when you're not measuring, the Schrödinger equation, and another completely different set of rules for when you are measuring, the collapse postulate. In many worlds, there's only one rule. The Schrödinger equation always applies. Everything is always quantum. There's no arbitrary division between the quantum world and the classical world. The classical world emerges from the quantum world through decoherence and branching. Yes, but I think that's right. What do you think are the problems with many worlds? The biggest problem is, I think, people's struggle to deal with sort of the infinity that it brings forth. The sheer number of parallel universes, the vast multitude of branches, every quantum event creating new splits, new versions of reality. It's overwhelming. It's hard to wrap your mind around. But I don't know that that's necessarily an argument against it. Just because it's hard to imagine doesn't mean it's not what's happening. Reality doesn't care whether we find it intuitive or comfortable. The universe is under no obligation to make sense to us. If many worlds is right, everything changes. The conflict between quantum mechanics and relativity vanishes. One of the deepest problems in theoretical physics simply disappears. Physicists have been struggling for decades to unite quantum mechanics with general relativity to build a theory of quantum gravity. This is the holy grail of theoretical physics, the ultimate theory that would explain everything from the smallest particles to the largest structures in the cosmos. But we've been failing. We've made progress. We have candidate theories like string theory and loop quantum gravity, but we don't have a final answer. We don't have a theory that definitely works. And maybe we've been failing because we've been trying to marry relativity to a non-local theory. We've been trying to combine Einstein's local theory of gravity with the Copenhagen interpretation of quantum mechanics, which is fundamentally non-local. That's like trying to fit together two puzzle pieces that were cut from different puzzles. They don't match. They can't fit. But if quantum mechanics ultimately turns out to be local, if many worlds is the correct interpretation, well, then Einstein's dream of a local description of reality might not be dead after all. It might just be waiting for us to understand it properly. Let me take you deeper into why this matters so much. General relativity is built on a foundation of locality. Every point in space-time is only directly affected by its immediate neighbors. Gravity propagates as ripples in space-time, spreading outward at the speed of light. Information flows from place to place, never jumping across gaps. This is the core principle of relativity, and it's been tested to extraordinary precision. We've detected gravitational waves from colliding black holes billions of light years away, and they traveled at exactly the speed of light, just as relativity predicts. Relativity is local, and it works beautifully. But when physicists try to make gravity quantum, try to apply quantum mechanics to the fabric of spacetime itself, they run into terrible problems. The equations blow up. They give infinite answers that make no sense. And many physicists suspect that part of the problem is this tension between the locality of relativity and the non-locality of quantum mechanics. If quantum mechanics really is non-local, if it really does involve instantaneous influences, then how do you make that compatible with a theory where nothing can be instantaneous? How do you quantize a local theory using a non-local theory? It's a fundamental mismatch, but many worlds offers a way out. If quantum mechanics is actually local, if the non-locality is just an illusion created by our limited perspective, by our inability to see all the branches, then maybe quantum gravity becomes possible. Maybe the puzzle pieces do fit after all. We just had one of them upside down. This is speculative, of course. Many worlds doesn't automatically solve quantum gravity, but it removes a conceptual obstacle, a philosophical barrier that might have been blocking progress. It suggests that maybe we've been thinking about the problem wrong all along. Now, let's address the elephant in the room, the thing that makes most people reject many worlds immediately, the sheer extravagance of it. Every quantum measurement splits the universe. Every quantum event, every interaction between particles creates new branches. And quantum events are happening everywhere, all the time. Trillions upon trillions of them every second in every cubic centimeter of space. Each one spawning new universes, new branches, new versions of reality. The number of parallel universes grows exponentially, explosively, beyond any number we could write down or comprehend. It's an infinity of infinities, a cosmos of unimaginable vastness. This seems wasteful, absurd, ontologically extravagant in the extreme. Surely nature wouldn't be this excessive. Surely there's a simpler explanation. But here's the counter-argument. Many worlds doesn't actually add anything to the theory. All those parallel universes, all those branches, they're already there in the mathematics of quantum mechanics. They're already in the Schrödinger equation. The wave function describes all possible outcomes, and they're all present in the wave function simultaneously. Copenhagen says that most of them disappear when you measure, that the wave function collapses and only one outcome survives. But that's adding something extra, an additional mechanism, a new rule that has to be imposed by hand. Many worlds doesn't add the parallel universes. It just refuses to delete them. It takes the mathematics of quantum mechanics seriously, literally. It says that if the Schrödinger equation describes multiple outcomes, then those outcomes are all real. We shouldn't arbitrarily delete the parts of the wave function we don't observe. That's not simpler, that's more complicated. You're adding a collapse mechanism that isn't in the fundamental equations. So, in a strange way, many worlds is actually the more conservative interpretation. It's what you get if you just take quantum mechanics at face value without adding extra assumptions. But there's another objection, a more practical one. If all these parallel universes exist, why can't we see them? Why can't we interact with them? Why does it feel like only one outcome happens when we make a measurement? This is explained by something called decoherence. When a quantum system interacts with its environment, when it becomes entangled with the vast number of particles around it, the different branches of the wave function become effectively isolated from each other. They can no longer interfere. They become separate worlds that can't communicate or influence each other. Decoherence happens incredibly quickly for anything larger than microscopic particles. For a measuring device, for a person, for anything interacting with air molecules and light and heat. Decoherence happens in a tiny fraction of a second. This is why we don't see superpositions in everyday life. This is why it feels like only one thing happens. The branches split and separate so fast that each version of you is completely unaware of the other versions. You can't see the other branches because decoherence has made them invisible, unreachable, isolated. They're still there, still real. But you can never interact with them. So Many Worlds makes a prediction. It predicts that you should observe quantum interference effects, quantum superposition, only for systems that haven't decohered yet, systems that are still isolated from their environment. And this prediction is testable and has been tested. Scientists have created larger and larger superpositions, more and more complex quantum states, and they've shown that once these systems interact with their environment, the interference disappears. The quantum behavior vanishes. This is exactly what Many Worlds predicts. It's not proof that Many Worlds is right, but it's consistent with it. The theory makes predictions, and the predictions match experiment. Now, let me show you something remarkable, something that connects back to Bell's theorem in a surprising way. Remember how Bell proved that any local theory must predict at least 33% disagreement when measuring entangled particles at different angles. And quantum mechanics predicts 25%. Well, in Many Worlds, we need to think about what disagreement even means. When you measure your particle and get plus, there's another version of you that got minus. When your friend measures her particle, she also splits. So there are now 4 versions total. One version of you with plus and one version of her with plus. One version of you with plus and one version of her with minus. One version of you with minus and one version of her with plus. One version of you with minus and one version of her with minus. From the perspective of any individual branch, any individual version of you and your friend, you see the usual quantum correlations. You see 25% disagreement. But from a God's eye view, from a perspective that can see all branches at once, something interesting happens. The correlations are there not because of faster-than-light influences, but because of how the branching structure is organized. The wave function evolves locally, following the Schrödinger equation. and the branching creates patterns that look like non-local correlations to observers within any single branch. This is subtle, and it's controversial. Some physicists argue that many worlds doesn't really solve the locality problem, that the correlations still require some form of non-locality, just hidden in the wave function structure rather than in collapse. Others argue that many worlds genuinely restores locality because no information ever travels faster than light in any branch. The wave function itself is not a physical thing that travels, it's just the mathematical description of what exists. This debate is ongoing, and I don't want to pretend it's settled. Many worlds is not a perfect solution, and it has its own conceptual problems, but it's a serious possibility, taken seriously by serious physicists. Let me tell you about another interpretation that's also non-local, but in a different way. The pilot wave theory that John Bell championed. In this theory, particles always have definite positions. The electron is always at some specific location, not spread out in a cloud of probability. But it's guided by a wave, the quantum wave function, which really exists and influences the particle's motion. This wave can extend across vast distances, connecting entangled particles. When you measure one particle, you disturb the wave, and that disturbance instantly affects the other particle through the wave. It's explicitly non-local, but at least you have a clear picture of what's happening. The pilot wave theory makes exactly the same predictions as Copenhagen quantum mechanics for all experiments. It's empirically equivalent. You can't do an experiment to distinguish them because they always agree on what you'll observe. So why don't we just use pilot wave theory instead of Copenhagen? Why did it get rejected and forgotten for decades? Partly because of sociology. Bohr was so influential, the Copenhagen interpretation was so dominant, that alternatives were dismissed without serious consideration. But partly because pilot wave theory seems more complicated. It has particles and waves, two separate things, whereas Copenhagen just has the wave function. And it's explicitly non-local, which bothered people even though Copenhagen is also non-local once you think about it carefully. But Bell showed that the non-locality objection doesn't hold water. If any theory has to be non-local, as Bell proved, then you can't reject pilot wave theory for being non-local. That's not a flaw, it's a necessity. And the apparent complication, having both particles and waves, might actually be a virtue. It gives you a clearer picture of reality. It answers questions that Copenhagen refuses to answer. Where's the electron when you're not looking? In pilot wave theory, that question makes sense and has an answer. The electron is wherever the pilot wave guides it. Simple. So we have at least three interpretations of quantum mechanics. Copenhagen, where wave functions collapse non-locally, and we can't ask what's really happening between measurements. Pilot wave theory, where particles have definite positions guided by a non-local wave. And many worlds, where wave functions never collapse and reality branches into parallel universes, possibly restoring locality. All three make the same experimental predictions for any experiment we can currently do. So, how do we choose between them? How do we figure out which one is actually right? This is one of the most frustrating situations in physics. We have this incredibly successful theory, quantum mechanics, that makes astoundingly accurate predictions. But we don't know what it means. We don't know what it's telling us about reality. And different interpretations give radically different pictures. Is there one universe or many? Are particles really waves or guided by waves? Do measurements cause collapse or just split the universe? These aren't just philosophical questions. They shape how we think about reality, how we approach new problems, what kinds of theories we try to build. Some physicists say it doesn't matter. As long as the predictions are the same, the interpretation is just a matter of taste. Shut up and calculate. But that attitude might be holding us back. Maybe we can't build quantum gravity because we don't understand what quantum mechanics really means. Maybe the interpretation matters more than we think. Maybe asking these questions, taking them seriously, is exactly what we need to make progress. That's what John Bell believed. That's why he spent his life fighting against the shut-up and calculate mentality. Let me bring this back to our original question. Have we found a way to travel faster than light? The answer depends on what you mean by travel. In the Copenhagen interpretation, yes, influences travel faster than light when wave functions collapse. Information about a measurement here instantly affects the wave function there. But you can't use this to send messages, to communicate, because the outcomes are random. In pilot wave theory, yes, the pilot wave connects distant particles instantly, creating correlations faster than light. But again, you can't control it, can't use it to send information. In many worlds, the answer is more subtle. No single thing travels faster than light. The wave function evolves locally according to the Schrödinger equation. But reality branches, splits, creates parallel versions of everything. And from the perspective of observers in any single branch, it looks like there are faster-than-light correlations. The appearance of non-locality without actual non-locality. The illusion of instantaneous influence created by the branching structure of reality. Or maybe it's not an illusion at all. Maybe it's a different kind of non-locality that we don't fully understand yet. Here's what we know for sure. Bell's theorem proves that quantum mechanics, in any interpretation, must have some feature that seems incompatible with our intuitive understanding of locality. Either there are genuine faster-than-light influences, or reality is branching into parallel universes, or something equally strange is happening. We can't escape into a simple, local, single-universe picture where everything makes intuitive sense. Nature won't let us. The experiments have spoken, and they tell us that reality is weirder than we wanted it to be. Einstein spent the last decades of his life trying to prove that quantum mechanics was wrong, that there must be a deeper, local theory underneath. He failed. Quantum mechanics is right, but he was also right to be concerned. He identified a real problem, a genuine tension between quantum mechanics and relativity, and that problem still exists today. We still don't know how to reconcile quantum mechanics with general relativity. We still don't have quantum gravity. And maybe, just maybe, the solution will come from taking Einstein's concerns seriously, from finding an interpretation of quantum mechanics that's genuinely local, or from understanding how to make sense of non-locality in a relativistic context. The story isn't over. Bell's theorem opened a door, showed us that these questions are physics, not philosophy, that they can be tested experimentally. But we still don't know what lies on the other side of that door. We don't know which interpretation is right. We don't know how to build quantum gravity. We don't know if locality can be saved or if we have to abandon it. These are open questions, active areas of research. The next chapter of this story is being written right now, in laboratories and on blackboards around the world. And here's the most exciting part. The answer might change everything. If many worlds is right, and quantum mechanics is actually local, that could revolutionize how we think about quantum gravity. It could open new approaches, new possibilities that we haven't considered, because we were stuck thinking about quantum mechanics as non-local. If instead Copenhagen or pilot wave is right, and non-locality is real and unavoidable, then we need to figure out how to incorporate that into our theories of spacetime and gravity. We need to understand how faster-than-light influences can exist without creating paradoxes, how they fit into the relativistic universe. Either way, understanding what quantum mechanics really means, which interpretation is correct, could be the key to the next revolution in physics. It could be what finally allows us to unify quantum mechanics and relativity, to understand the beginning of the universe, the interior of black holes, the nature of space and time themselves. These aren't abstract philosophical questions. They're the questions that will shape the future of physics. And it all comes back to Einstein's simple observation in 1927 that measuring an electron here seems to instantly affect the wave function there.